Hello AP Mechanics students. Welcome to our second review lesson on Newton's laws. Now Newton's laws, as I said during the year, Newton's laws are really the heart of the course. Everything we learned this year is centered on Newton's laws. The kinematics unit, the forces unit, they were getting us ready so that we could understand Newton's laws. Then we learned Newton's laws, and then from there we learned about energy, momentum, rotational motion, simple harmonic motion. All of those are just different manifestations, different ways to represent Newton's laws. So this is the most important topic in the whole course. It is the heart of the course. You can also see that today the review is going to be pretty long. We got a lot of things to review, a lot of concepts, a lot of different kinds of problems, different techniques to Newton's laws. So we're going to first review Newton's three laws. Then we're going to learn about active accelerations, like when a runner starts accelerating forward, picking up speed. But a runner, we could pick any animal, a horse, for example, or any machine like a car, motorcycle, a bulldozer that has its own means to acceleration, either muscles or motors. Passive accelerations, vertical acceleration, inclined planes, different kinds of multi-body systems, trains, Atwood machines, so on and so forth. Then we're going to briefly I'll mention some things about how calculus comes into play with Newton's laws, and also a little bit about 2- and 3-dimensional motion systems that move in 2 or 3 dimensions. So that's what's coming. Again, you don't have to jot this down because it's what's coming in the rest of the notes. Okay, so alright, here is the first page. So briefly, Newton's three laws, 1, 2, 3. You don't have to remember which is which, as far as I know. Maybe someday they'll ask, what is Newton's first law? But you don't have to distinguish. You don't have to know that this law is Newton's first law. You just have to know that objects at rest stay at rest unless acted upon. So actually, I should have said Newton's first law is actually 2 sentences. That's the first one, okay? The second sentence is that objects in motion stay in motion unless acted upon. So the at rest part, as I mentioned when we first learned this, most people, even people who don't know any physics, know that things stay at rest unless you push or pull on them. The thing that even messes up physics students who've studied all year is the objects in motion part. Most people will eventually somehow get tripped up on this idea that things have to have a force to keep them moving, and that is false. Things move with zero force. They need a force to stop them, okay? So when you roll a ball on a sidewalk, there's friction that stops it. If you could remove this friction or the sidewalk and do this in outer space, the thing would go forever. All right, so that's the idea there, and I'll mention that in motion part later when we look at something slowing down. The second law is the equation when A equals F net over M. So that's the formula, but it's really 2 concepts. One is that more force creates more acceleration, and the other is more mass creates less acceleration. And the variables are to the 1 power. Also, you need to know that the acceleration expressed with calculus is dv dt, or the second derivative of the function of position with respect to time. The third law is again a concept like the first, and usually it's stated in books, for every action there is an equal and opposite reaction. I like to state it this way because it's clear and it always gives the concept in a form that you basically can't go wrong if you remember Newton's third law this way. Not as catchy, not as poetic sounding, but any 2 things touch. If A pushes B with some force, B pushes right back on A with the same force. It doesn't matter what is the active agent and what is the passive agent. In other words, you could punch your friend joking around in the arm, boom, hey, how you doing? And you say, well, wait a minute, the friend's not doing nothing, they're relaxing. But if you push them with 20 pounds, the friend pushes right back with 20. Okay, and that's a law of nature. Any two things interacting, the forces of one on the other equal to the other right back. Okay, so those are the concepts. Now let's look at the applications. So the first kind of phenomenon we're going to study is active accelerations, a runner, a car. So in the case of people or animals, we have muscles and skeletons to keep us, to create force. But in the case of machines, obviously it's motors and gears and whatnot. So something in the object can cause its own acceleration. So here's a runner, and the thing that's important to realize is the objects are always interacting with the Earth. If you put this runner or the car in outer space, maybe the wheels just spin and it doesn't go anywhere. So you always need a second object, a second body, in this case the Earth. So it's really an interaction between the runner and the Earth, speeding up. Runner's muscles clench, and then what happens? Well, when they clench, what happens is they push the Earth back. So this is the force diagram on the Earth. So again, third law, runner pushes Earth back, Earth pushes runner forward. Okay, so that's the forward force coming from pushing the Earth back, and it's friction, right? You grease up the surface here and the runner slips and they don't go anywhere. So it's friction that's pushing the runner forward and making them speed up. I mentioned this when we studied this. A lot of students have a misconception. Friction always slows things down. No. On the Earth, as it's often speeding objects up also. But here are the other vectors. Obviously, the runner, we all understand, most of us understand that the runner's pulled down with the force of gravity. But what a lot of people don't get or don't know is that if the runner's pushed down, I'll use pounds because that's what we're more familiar with. Maybe the person's a 200-pound runner. That runner is pulled down by the Earth with 200 pounds, but the Earth is pulled up by the runner with 200 pounds. Doesn't matter which is bigger, which is stronger. Newton's third law, right? So Earth pulls runner down with 200 pounds. Runner pulls Earth up with 200 pounds. Okay, so that's the interaction there. So gravity, I color coordinated the action-reaction pairs and the friction action-reaction. Now, the runner doesn't fall because the road surface or whatever they're on, which is part of the Earth, is supporting them with a normal force. So Earth pushes runner up, runner pushes Earth down. Action-reaction. So most of the time, you don't have to know this part. I'm just kind of showing you where all those forces came from. It's here, the key idea. Gravity, normal force balancing, and then the forward force is friction. Okay, so how do we mathematically then analyze this? We use Newton's second law, which we're going to use time and again throughout today's very long notes. A is F net over m. If you look at the force diagram, the net force, the unbalanced force, is just that friction force. That's what goes in for F net, the force of friction, divided by the mass of the runner. Now, what is that force of friction coming from? The legs of the runner. So it's based on the effort. If the runner pushes back 100 newtons, they get 100 newtons in the forward direction. Runner works out, gets stronger. Now their legs are able to push 200 newtons. They get 200 back. So that's the effort of the runner. That's what goes in for F net. Or it could be, if you want to know the maximum acceleration possible for the runner or a car or whatever, it's the limit of friction. So this would give you the maximum acceleration possible by using mu static F normal. Plug that in, you'll get the maximum force over mass, gives you maximum acceleration. Or if the car or the runner burn out, in other words, the engine or the legs of the runner are so strong, or the engine of the car, that they push back with more force than friction can push back with, or the Earth can push back, so they burn out, then no matter how strong the engine or the legs of the runner are, the forward force is going to be mu kinetic times F normal. So you could plug that in and get the acceleration at burnout. So those are the possible numbers you plug into this F net over here. Now when the runner slows down, what the runner does, again, interacts with the Earth. In order to slow down, the runner, instead of pushing backwards like over here, the runner pushes the Earth forward so that the earth pushes the runner backwards. And we got gravity and normal force the same. This is where very often when we did practice problems, even after studying Newton's laws for a month, remember, I don't know if you remember, half the class put a forward force here. They said, well, but what's pushing the runner forward? That's the runner's inertia pushing him forward. No, inertia is not a force. It's a tendency. It's what the runner, what his body does without any force at all. So without that friction, the runner would be maybe in like in outer space or something without, and coasting forever. Okay? So you need a backwards force to stop. And people also then might think, well, when the runner crashes into me, I feel a forward force. That's the runner's inertia. Well, no, that's the runner pushing you forward and you push the runner backwards. So when something is slowing down and you experience something receiving a forward force, it goes on the other object, not on the runner. If we put a forward force here, then the net force is 0. The runner keeps going at a constant velocity, never slows down. So the calculation's simple on the runner car problem. The other phenomenon we're going to study or review is the passive acceleration. And what do I mean by something passive? Something without a motor or muscles, like a box or a crate or something like that. The simplest case is that you pull the box or crate in a forward direction. Then what happens, we got gravity, the earth pulling down on the box, normal force pushing up, balancing it out. And I should have said this in the previous force diagram. Remember that you have to label this Fg, not mg. Because if you label this mg, this is also mg. Mg is the magnitude, the number of newtons of that force. So you need to label what it actually is, its name, which is it's a force of gravity. And this is the normal force, both mg. But that label is critical. You don't have that there, you lose points. Okay? And then forward force you're pulling, and then there's friction because we're dragging it over some kind of surface. So Newton's second law, A is F net over m. These two create a net force of 0. They don't enter into Newton's second law. So again, if this were a test, you know, you'd write out the Newton's first law first. Okay, Newton's second law first. A equals F net over m. I'm showing you the highlights in this video. So I'm trying to be brief on a video that's already going to be very long. But so this is just the key here. You want to look at where this came from, study this, and know that later when it's time to solve problems on the AP, you need more steps, right? You got to show things. But this is the key thinking, showing you the thinking. The forward force minus the backward force, mu mg, all over the mass. And why is this mu mg? It's friction. Mu f normal. Normal force being mg. So that's mu f normal. Another thing I want to point out, if the forward force is equal to the force of friction, most people would say, okay, you got same newtons forward as backwards, maybe 10 and 10. Okay, it's at rest. A lot of people would say that, and it's possible that it's at rest. But if you understand the physics, you know that it could also mean it's going at a constant velocity. 10 newtons forward, 10 newtons backwards means not zero velocity. It means zero acceleration, which might mean steady, steady, steady forward motion. So keep that in mind, that when the force is balanced, it doesn't mean the object's necessarily at rest. It could be moving at a constant velocity. All right. And they'll often complicate this situation a little bit if you pull up instead of pulling directly horizontally like in the previous analysis. This is the force diagram. We still have Fg down. This is now up at an angle. We still have normal force because it's resting on the surface, but this normal force is shortened. It's not equal to mg. Why? Well, let's suppose you're a 100-pound person and you're standing on a bathroom scale. And I come over here and I pull up. I really am pulling up because this has an upward component. Then the scale reading would go down. Let's suppose you're a 100-pound person and I pull up with 20. The scale reading would only be 80 pounds. That's the normal force. And because there's a normal force, there's a force of friction. Now, how do we analyze this in terms of Newton's second law? I already kind of got into it a little bit, but this force, we could think of it as having components. You're not allowed to draw components on the AP when they ask you to draw a diagram. You would lose points. So I'm just going to put this little shaded triangle here because I don't want to draw them in. AP test, you got to have only that. You draw these little components in and you're going to lose points. But you visualize them. So that's what the green triangle is there, because this is what's happening in my mind. I see that a force up in this direction could actually be thought of as a force pulling horizontally and vertically at the same time. This horizontal part, this is the hypotenuse F, and this is theta. So this is F times cosine to give me the adjacent side of the triangle. That's the forward force pulling this in that direction. F cos theta, right there. Forward minus backwards, friction. This whole piece is the friction force, mu F normal. But the normal force is not mg like in the previous part of the problem, which is off the screen right now. It is the gravity down minus this upward part as I mentioned. So this is mg minus the opposite side, which is the F sine theta. mg minus F sine theta, this opposite side gives me the normal. Like I said, 100-pound weight and I lift up on you with 20, the scale reading's only 80 now. So that's what this is, okay? All over the mass. Forward force minus backwards force, friction, all over the mass is the setup there. Again, you had to write A equals F net over M, and maybe you have to simplify this with numbers. I'm not showing details today, only setups, okay? Because again, this is where you're going to get most of the credit anyways, okay? Even if you don't get the answers, you hit the wrong things on a button, you set this up, chances are you might get 3 out of 4 points on this problem. And remember, 3 out of 4 is a 75%. That means you got like a 5 out of 5 on this problem. You didn't even get the answer. Okay, so these setups are really the important thing you want to focus on when you study. Another possibility is rather than pulling up like this, right? Okay, pulling up like this, I push down with a stick. So this is the stick, and I have an arrow because I'm pushing this down and making it go forward. This is how the force diagram changes. So this arrow, instead of being up like over there, it's pushing in. I drew the gravity vector shorter than before, but maybe it's the same box. The reason why, because I don't want to draw this so long right off the edge through here. But basically now, since I'm pushing down with a component, right? So again, you can't draw these in here, but you have to visualize this little triangle right here. So this is like the opposite situation. Let's suppose you're a 100-pound person and I come down and push down on your shoulders with 20 pounds. The scale reading is going to be 100 plus the 20, 120, right? So the normal force increases because you're pushing this in like that. So again, on the AP, you have to draw this and that's it. Don't add anything unless you want to lose points, which you don't, right? So that's there. Now, setting up A equals F net over M. Here's the forward part. That's the F cos theta because it's the adjacent side. This is the hypotenuse. F cos theta right there, forward. Minus mu F normal, friction. That's this force. Forward minus backwards. Forward minus backwards. Now, the normal force this time, as I said, is your body weight plus this y component F sine theta. mg plus F sine theta. That's all normal force times coefficient gives me friction all over the mass. Again, there's the setup for the acceleration there. Notice the difference, only a minus versus a plus. Whether you're pulling up, then it's a minus here, pushing down plus. But I wouldn't try and memorize that. Again, I'm just pointing that out for understanding. You got to understand these, and then your thoughts will then generate the solutions later. All right, so moving on to 4. Okay. All right. Vertical accelerations. Okay. So vertical accelerations, things like rocket ships or people standing in elevators are a couple examples of vertical accelerations. So there's 4 different scenarios. One is acceleration 0, one is acceleration upward, one is acceleration downward, less than 9.8, and another one is acceleration downward greater than 9.8. All different force diagrams. So, when your acceleration is 0, from A equals F net over M, 0 equals F net over M means F net has to be 0, which means forces have to balance. So the earth is pulling down, and if you're in an elevator, the floor is pushing up. Or if you're a rocket, then your upward thrust of your engines is the same as your weight. By the way, the thrust works by Newton's third law. The rocket pushes the gases, the flame downward. The gases of the flame push the rocket back upward. But anyways, that's a little side thing, not really going to probably show up on the AP. But so the forces are balanced. Again, people who don't understand physics very well will say, oh, that's the person standing in the elevator not moving. And you have to realize, yes, that is a possibility. But there are two other possibilities. The elevator is moving up at a constant speed, or the elevator is moving down at a constant speed. Same force diagram. People, oh, that's not moving. No, it could be moving, okay? With zero acceleration, constant velocity. Okay? So you're in this elevator, a 100-pound person, your feet would feel, your legs would have to generate forces of 100 pounds, or the elevator's pushing you up. That's what you perceive with your feet and your legs. The other next possibility we're going to look at is the acceleration is now in the upward direction, and now if there's an acceleration, there has to be a net force. But the first thing, before I point at anything else about forces, upward acceleration, most people will know that that means the object, like you in an elevator, is moving up toward the top of the building and speeding up. That's upward acceleration. Not as many people will know that that means, or remember that it means, you could also be moving down but slowing down, and that's upward acceleration. You're moving down, but your acceleration is the opposite way, so you're accelerating upward, okay? All right, so what you have to do is draw this arrow longer than that one, and on the AP, you want to generally draw arrows so that you're showing that you understand which forces are bigger. So since that's bigger, you have to draw a longer arrow. If you draw it the same size, they may take points off. Now, does it have to be exactly the same percentage longer than this is, according when we answer? No, just longer, okay? So that you're telling the exam reviewer or the evaluator that you understand the physics here. There's more upward force than downward to get an upward acceleration. So the way to set up A equals F net over M, just always in an elevator problem, just do the bigger force minus the smaller force. Otherwise, if you start thinking about down always negative, you're going to get messed up eventually. So just A is the forward force minus the backwards force, the gravity, mg, all over the mass. What's unknown here? Maybe the acceleration. They tell you a person is 100 kilograms, and so their weight's like 1,000, and they experience 1,200 Newton upward force. 1,200 minus 1,000 over 100 kilograms gives you the acceleration, right? So maybe this is the unknown. Or they say a 100 kilogram person, so that could go here and here, is accelerating up at 2. What's the normal force? Okay, so that's basically, pretty straightforward in terms of solving. Not as difficult as some of the other Newton's law problems. Okay, acceleration is down, but less than 9.8. So that's when you're accelerating in an elevator downward, your accelerations are always going to be less than 9.8, never greater than 9.8. Again, most people would say, okay, acceleration down, that means the object's moving down and speeding up. That's downward acceleration, okay? And it can be. Not as many people would realize that the elevator could be moving up and slowing down, and that's downward acceleration. Why? You're moving this way. To slow down, you need acceleration down, okay? Opposite way. So the force diagram, draw the gravity bigger. Draw the gravity the same size as over here. It's still the same person, 1,000 newtons, 1,000 newtons. But instead of, say, maybe 1,200 up, maybe we only have 800 up. So now we have 1,000 down, 800 up. Net force down, the object will accelerate down. So how do you set that up? Again, you write A equals F net over M, and then the second line, A equals the forward force, mg gravity, minus the backwards, the normal force over M. And same thing about either this being unknown or that being unknown, and then you solve. One other possibility, not very common, but I just threw it on here just in case it comes up. Acceleration is down but greater than 9.8. So the example of, or when you might have experienced this is at an amusement park, if you ever went on the ride called the Tower of Terror. I believe that ride pulls you down greater than 9.8. So your weight is here. The Earth's pulling you down with that same, if 100 kilogram person, this is 1,000 newtons again. But now the shoulder pads, because it can't be under you, right? If you're accelerating down greater than 9.8 on a regular elevator, your feet would just lag behind and you would be like floating above the floor. Not really. You'd just be falling slower than the floor, so there'd be a separation there. So what happens is the pads on your shoulders in that ride push you down. And so now the acceleration is the two downward forces added together over the mass. And maybe instead of 9.8, you get like 12 or something like that, or 14 acceleration in downward direction. All right, so vertical accelerations, okay, the 4 situations. The next situation, and by the way, if you feel like this is too much, pause it, go for a walk, maybe go get something to eat and come back. Don't overload here. Pace yourself with the knowledge. Maybe I should have said that at the start of the video. So take a little break. If you feel like keep watching this on and on, you're not going to remember it anyways. We're trying to remember this, obviously. So do what you need to up your retention. Inclined planes, fancy way to say hills, objects on hills. There's 3 different situations we're going to look at. When something is sliding down a hill, sliding up a hill, or when there are extra forces acting on it while it's on a hill. So sliding down a hill, maybe this is you in a sled in the wintertime, so you're sliding down. Sliding up a hill, maybe you just came down a giant hill here, and then you went up a little one, so you're on your way up, but nothing is pushing you. You just have velocity, so you're sliding up, okay? Coasting freely upward. Okay, so the force diagrams. On an inclined plane, there are 3 forces, okay, if there's nothing pushing from the outside. The Earth pulls straight down. Planet Earth doesn't suddenly say, oh look, the person's on a hill sledding, so I'm going to pull now in a different direction. No, the Earth blindly pulls straight down. Again, a 100 kilogram person, this will be 1,000 newtons straight toward the center of the Earth down here. The normal force is perpendicular to the hill, normal, perpendicular, preventing the sledder or whatever is on the hill from breaking through the ground surface or the ice or whatever. And then, of course, nothing or very few things are perfectly frictionless. So there is friction even though we're dealing with snow or even ice. Those are the 3 forces. So, to analyze this, we need to use Newton's second law, A is F net over m. We've got to figure out what the forward force is, what the backward force is, subtract them, and divide by the mass. The way to do that is to draw, is to imagine components of this downward gravity force. So once again, I got my little triangle here. I don't want to draw them in because I lose points on the AP, so I'm visualizing this, okay? This is only in my mind, that little triangle there. And I see that this gravity vector could be thought of as a hypotenuse of a triangle with one leg lining up with the hill and the other leg perpendicular to the hill. Now if this is theta, and again I'm not going to prove that, theta's here, when we learned this in class I said, I showed how you could figure that out, and then I just said, but if you just remember that, that's perfectly fine. So theta goes in the bottom there. So this component is what's pulling the person down the hill. We call that x. Even though it's not lined up this way, we call it x anyways. So the x-axis goes this way. This is the y-axis. This component here is balanced by the normal force. And if this is theta, that's the opposite side. This is mg sine theta right here. And this is the adjacent side to theta. This is mg cos theta. Okay? So, forward force minus backwards force. The forward force is mg sine theta minus the backwards, which is friction. That's the backward force right there. So friction is mu F normal. And the normal force, as I said, is this y component, the adjacent side, mg cos theta. Hypotenuse times cos theta, that's the normal force. Forward minus backward friction all over the mass. When something is sliding up the hill because it has velocity, so remember, nothing is pushing it up the hill. Again, that's what I said. A lot of students will think that because they think of inertia as a force. They don't realize Newton's first law. Galileo realized, no, objects stay in motion with zero force. They require a force to stop them. So this moving upward, there's no force pushing it up in that direction. It's coasting with its natural tendency to stay in motion. So gravity still is down toward the center of the Earth. Doesn't change just because now you're sliding up the hill. The Earth just pulls down with 100 times 9.8 or 10 or 1,000 down. That's down. But this time, instead of friction being up the hill while we're sliding down, it's down the hill because we're sliding up, so it's going to go the opposite direction. And the normal force is the same in this scenario. Once again, these are the only three forces. AP test, you can draw this. Okay, and I should have said before, if you want to draw another diagram off to the side with components, you're welcome to. But this is the place where they say on the dot provided, draw the force, and they say that, all that business. So when you do that on the dot provided, that's where you don't draw components. In the margins, you're welcome to draw whatever you want, components, no components, whatever. But this is what we visualize again. Down the hill mg sine theta, perpendicular to mg cos theta. So now you see that this down the hill component of mg sine theta, is lined up with friction, whereas over here was opposite. So together, they're both creating a deceleration because it's sliding up the hill. So if they're working together, no minus sign like we had over here when they were fighting each other. Here, downhill, plus sign. They're working together to produce a deceleration over the mass. Okay, so that's sliding up the hill. Same analysis, except with a plus sign because friction flips the other way. All right, this is not very common, extra forces. In fact, if you're feeling like you're burning out, go ahead and skip this. Go forward a couple minutes. Like I said, AP is a game of just trying to get more than 2/3 of the test correct. Looking at the main concepts. Inclines, these, I wouldn't skip those. Okay, those are more essential. This, if you feel like you have plenty of energy, go ahead, let's continue on with this one. So this is like the same situation, but this time maybe I have a pole like this and the hill's like this, and I'm pushing the person up the hill with a pole directly horizontally, not up the hill like this, but horizontally. I could do up the hill like this and we could analyze that, but again, I can't review everything. So I'm pushing this way, and now the object is accelerating up the hill, and I want to find the acceleration as it's accelerating up the hill. So this I think of as having components again, mg sine theta down the hill, mg cos theta perpendicular to the hill. But this also has a component into the hill just like this one. So this is F sine theta, whereas this is mg cos theta. Those together produce the normal force. The y component of gravity and the y component of this applied force are the normal force. And then there's friction down the hill because it is accelerating, moving up the hill. So what's accelerating this up the hill is this horizontal part of this force, which is adjacent to the angle. So it'd be F cosine theta is this here, accelerating it forward up the hill. Down the hill, I've got this x component of gravity, which is the opposite side, the mg sine theta, pulling in the opposite direction as that force up the hill. Minus mg sine theta. And then friction also, minus mu F normal. And this is the y component, mg cos. This is the y component, F sine, because it's the opposite side over here. So again, forward horizontal of F, backwards of the x component of gravity, backwards friction all over the mass. All right, so that's scenario, that setup. Let's look at 6. Okay. Multi-bodies. So we're going to look at a few different kinds of multi-body problems. The first one we're going to look at is a simple train. 3 objects, M1, M2, and M3, all connected with ropes, and then you pull forward on this rope, which is M1. So, the force diagrams. Okay, all 3 objects are pulled down by gravity. Again, the mg is not important. The fg is. On the AP, you better label these fg. You could even put fg1, fg2, fg3, but that's probably not even necessary. The fact that you know that it's gravity pulling down, that's the key. And, I didn't write masses, but, from the size of the object, this is the most massive one. Second least, so that's why I kind of draw the gravity proportional. The biggest one, middle one, least one. The normal forces upward balance each of the gravities. Balance, balance, okay? Holding the blocks up, that's the surface below, supporting them all. Now, obviously I'm pulling the train forward with this F. So this block 1 accelerates forward, and then suddenly this cord becomes tight. And that then results in block A, maybe I'll put, or block 1, pulling block 2 forward. We don't know what that force is, so I'm just going to call it T1. But Newton's third law, A pulls B forward, B pulls A right back. T1, T1, same tensions. I color coordinated the action-reaction pairs. That's a little short, that should be a little bit longer, but I draw them the same length. And then of course, since this is dragging over a horizontal surface, there's a little friction, force of friction 1. Now this block starts moving forward, that's why I have friction 2. Okay, so there's that. It's kind of hard, it kind of got overwritten by the other colored arrow, but there is a backward arrow right there, force of friction 2. And so this block moves forward, and this cord now tightens up, and it starts pulling this third object forward with another unknown force, which we're going to label tension 2. But again, Newton's third law, law of nature, you cannot shut it off. If B pulls C forward with, 5 newtons, C pulls B right back with 5 newtons. So I color coordinated the action-reaction pairs there. And then there's friction in this object that is dragging over the surface. So what we do when we have multi-body problems like this, we write system of equations, MA equals F net for all the objects. And then we get a system of 3 equations with 3 unknowns. So I do MA equals F net for this object. MA is the forward force minus the 2 backward forces here. T1 is backward, and so is force of friction 1, mu F normal. This would obviously be the kinetic coefficient of friction. Second object, MA, M2A, is equal to its net force. What's its net force? We go back to the diagram here, and we see T1 is forward, and then we got 2 backward forces, T2 and force of friction 2. T2 minus mu F normal for the second force of friction. And then we do MA equals F net for the last object. MA, M3A, MA equals F net. And if you look at the diagram, 1 forward force, T2, 1 backwards force, mu F normal, mu M1G. And then we solve for the 3 unknowns. The easiest way is add the equations all up, and then all the tensions will drop out, and you can solve for the acceleration. I didn't show the details again, I'm showing you the main ideas. You have to be able to draw this and create a nice force diagram, and then you have to be able to create a system of equations. Those are the essential parts to get you most credit anyways. The answers might be 1 final point. Okay, but by the time here, the force diagram might be 4 points, this might be 3 points, 7 points, and then what? You don't get the last one because you didn't know. So this is not important. It's 7 out of 8 maybe, is all the other stuff. Again, as I mentioned when we first studied this, there is a shortcut. You can think of this whole train as one object. And so you put the forward force minus all the backward forces coming from the external. The tensions are not external. They're within the system, so they do not create acceleration. It's forward force minus all the 3 friction backward forces all over the total mass. So again, you think of it as one giant object, and you're welcome to do that and get full credit if you do it this way, by the way. Still have to be able to draw a force diagram though. All right, second multi-body is what we call Atwood's machine. It's a pulley which has negligible mass and negligible friction. Of course, in the rotation topic, we learned how to factor in the mass of the pulley. But right now, in this topic, we pretend the pulley is like made of very lightweight plastic, and these are like maybe big metal blocks. So this, doesn't really add much inertia to the system, so we ignore it. So we got obviously two gravity forces down. This is more massive, so it's going to descend. This is going to ascend because it's going to be pulled by this one. So, and then this is going to ascend because it's pulled forward by the first block, or actually M2. So Newton's third law still applies. B pulls A forward, then A pulls back B in the backwards direction with the same amount of force. Color-coordinated action-reaction pairs. Here I use the shortcut technique. I treat this all as one object. A is the forward force minus the backward force, all over the total mass of the system. And if it didn't ask for the tension, I could be done. But if it asks for the tension, then you do have to do MA equals F net for one of the objects. I picked this one. M1A is forward force minus backward force. All right, next situation. Okay, multi-body, or number 8, multi-body 3, the table and the pulley. Now we've got M1 hanging off the pulley, off the edge of the table with a pulley here, and M2 on the table. Maybe there's friction also. First thing I want to point out is that if the system is at rest, in other words, there's too much friction here, or too little mass here is another way you could think about it, then this is just hanging, and this is just, rooted because of the friction. The force of friction does not equal mu static times F normal here. A lot of students would just plug that in blindly. No, remember, static friction adjusts itself to be just the right amount to keep the object from slipping, the surfaces from slipping past each other. And what that means is that it's not mu F normal, it's less than that. First of all, the gravity here is balanced by the tension. That's what's here. And then that tension pulling here is balanced by the force of friction. So force of friction is actually the weight of this block, not mu F normal. But if there is an acceleration, then tension has to be less than the weight of this because it has to accelerate down. So let's say this is 10 newtons, maybe that's only 8. And now we got a net force of 2, and that goes down. So that's the diagram here for the hanging block. This block has the earth pulling down, M2G, and then the table supporting with that same normal force, the same magnitude of newtons of this gravity. But since action-reaction, so this is pulled forward by the hanging block with a certain number of newtons, not 10 newtons by the way, less, maybe 8 and 8. Otherwise, a lot of students say, oh, this is 10 newtons, that's 10 newtons pushing it forward. No, then this would not accelerate. It would have 10 newtons and 10 newtons, it would not go anywhere. So the tension always has to be less than the weight of this block for this to descend. So whatever it is, it's T, that's T, and then we got force of friction because it's a rough surface. I set up a system of equations in this case. MA equals F net for this object. M1A is the forward force, M1G, minus the backward tension. And then, same thing here. MA, okay, of this, forward force, minus the backward force. Once again, this is just a setup. Then you can do the details if this comes up on the AP. So that's 8. Move to 9. Multi-body 4, stacked blocks. So I have a horizontal surface here. I made it frictionless in this situation. Very often it is in AP problems, but it could have friction on the bottom. But on top of block 2 is block 1, which is held in place by friction. So I pull F over here and this two blocks accelerate. So here's the force diagram. So I'll do the top block first. The earth pulls this down, gravity, and then there's a normal force supporting it. Where does that normal force come from? It comes from the block underneath. So this isn't the table. It's coming from the block underneath. So once again, Newton's third law applies. Bottom pushes top up, top pushes bottom down. So this normal force, same, color coordinated for clarity. And then, since this is rushing off this way, this is being pulled along with friction again. So that's going to be the force of friction pull. But again, Newton's third law. A pulls B forward, B pulls A right backward. Action, reaction. Okay. And then the bottom block is also pulled down by gravity. So now it has two downward forces. The normal force, which comes from the weight of the top block, and its own weight. So the normal force at the bottom surface is the combined. And then the forward force. Okay, if there's no slipping, then you could think of this as all one system. And you could just say A is forward force minus backward, but there's no friction on the bottom surface. That friction is internal, so it doesn't enter into the system's acceleration. All over the total mass of the system. If the blocks are not slipping and they move together, just F over total mass. But sometimes they ask you to find the acceleration, the maximum force, F max, without, for there to be no slipping. So you pull, and these go together. Eventually, if you pull the bottom fast enough, it's going to pull out from underneath M1. So we're looking for that force where it's about to pull under. They're still moving together, but it's any harder that I pull, and this will pull out from underneath block 1. So the way to find that is first you analyze the top block as if to find its maximum acceleration. And the maximum acceleration comes when we have maximum friction, which is, mu static times F normal. Okay, mu F normal. So the maximum acceleration of the top block can sustain is mu static times G from here. Then I treat this all as one giant system again. So I do MA, take that acceleration. Maybe it's 0.8 times 10 or 8 meters second squared. I plug that in there. Times the total mass of the system gives me the total maximum force when they're about to slip apart. So let's suppose that comes out to be 40 newtons. But then I pull with 45. So again, that means the bottom block's going to slide out from underneath. How do I find the acceleration? Well, once again, I repeat and find the acceleration of the top block, which is friction over the mass, but this time it's kinetic friction because the blocks are slipping with respect to each other. So I have to use the kinetic friction value to find the slipping frictional force over the mass, gives me the acceleration of the top block. The bottom block has a different acceleration, its own acceleration. And I have to use forward force minus the backward force over the mass to get the acceleration. If I look back at the force diagram, the forward force is F and the backward is friction. So forward force F minus the friction, which is mu F normal, the normal force of only the top block, because that's the normal force that's creating the friction. And here I don't put M1 plus M2, because the blocks are not together anymore. So M2 is going to have its own acceleration. It has to be treated by itself. So we only put its mass there. All right, well, we're getting close to the end. So, almost an hour here. Newton's laws in calculus. So we went over this in differential equations our last unit, but basically what can happen is a couple different kinds of problems where calculus comes into play with Newton's laws. The first is you're given x as a function of time. Now, a lot of times when we had constant acceleration, we had x is 1/2 at squared. And that's a constant acceleration. So t to the second power. But in these problems, we might have x equals 5t to the third power, or fifth power, or seventh power. So we have a higher power of t than squared. And they'll tell you the mass in this higher power of x, maybe 2t to the fourth power. And they're asking what the net force is at a particular time. What you do is just say F net equals ma. Take the derivative of that x function twice. So if I have 2t to the fourth, I'd have 8t to the third is one derivative. 8t to the third, the second derivative will be 24t squared. That's what goes in here. Just take the derivative twice, multiply by the mass, you get the net force. That's pretty straightforward. Usually Newton's laws, if it's that kind of application, most students are fine with that. The other possibility is that I tell you the net force is a function of time. All the examples we just did, the net force was just a number. Forward force minus backward force. 10 newtons forward, backwards 8, 2. And we had an acceleration of 2 over the mass. But now maybe it's a function instead of 2. Maybe it's 2 times t squared. That's the net force. So I'm asked for the velocity. I can't use v equals v0 plus at. Those are only for constant accelerations. What I have to do is I have to say the acceleration, dv dt, is that force function divided by the mass. Then I separate the variables. I bring the dt over here, just have dv all by itself, and f over m now has a dt with it, and I integrate both sides and plug in limits v0 to v final, 0 to t final. Boom, get an answer, okay, for velocity. So that's the general process of how calculus comes into play with Newton's laws. The final thing, not very common, pretty rare, acceleration in 2 or more dimensions. So you might be told the force in component form, 2 newtons in the x direction plus 3 newtons in the y direction, for example. You could find the acceleration by just taking 2 I hat plus 3 j hat and dividing by the mass. And then whatever fx over m is will give you an acceleration in the x direction. Whatever fy over m is will give you a certain y acceleration. So a certain meters per second squared this way, a certain meters per second squared that way. And you could find where the thing is using kinematic formulas for both. So it's just basically 2 Newton's law problems happening at the same time. One in x, one in y, maybe one in z also. And then you just use kinematics to find the net position, the x coordinate, the y coordinate, the z coordinate as a function of time. All right, so I think we're over 50 minutes. So a lot of information. Again, you might want to, look through your notes, copy them down, look through them again a couple times, and then hopefully, you get a good grasp of all the topics. I lost my little outline, but again, so we got Newton's 3 laws, we got active acceleration, runners and cars, passive acceleration, crates, then we studied vertical accelerations, right? Rockets and elevators, okay? Then we studied inclined planes today, okay? Multi-body trains, multi-body outwards machines, multi-body table and pulley, multi-body stacked blocks, Newton's laws in calculus, and 2D accelerations. All right, well, congratulations. Thank you for staying with me for almost an hour. And good luck on the homework, and I look forward to our next review lesson next time.